Thank you, Chris. And thanks for the preview. I'll just fill in a couple details on top of that. It's a pleasure to be back at JQI. Thanks to Alexei Gorshkov, who's not here, but for inviting me. And this is not a picture of Wisconsin, but if the Earth were a little bit flatter than it is this on, actually? It is, OK. And the skies were clearer than they actually are, and you got up on the tallest building on campus and looked in the right direction west, you would see these beautiful mountains that are in Montana somewhere. But the picture is meant as a metaphor for the goal that many people in the quantum physics community have, and which is shared by many people here, to be able to create quantum states in high-dimensional complex spaces, create entangled states, use those states for quantum information processing, for quantum communication, quantum enhanced metrology, perhaps eventually to learn something new about the division between classical and quantum descriptions of the world. These are grand goals at lofty heights. There's a very long way to go. We think we're on the road going in the correct direction, but this road sort of disappears halfway there. And hopefully, with support from these funding agencies, we can figure out how to pave this road and get it to the goal. So I want to tell you about things we're doing trying to head that way. And maybe let me start with a little background on many-body entanglement. There have been many experiments in the last couple of decades demonstrating larger and larger entangled objects. There's this very famous work from Eugene Polzik's group with macroscopic entanglement between billions and billions of cesium atoms in two different cells. Of course, the amount of entanglement per atom is rather small. And there's indeed been many experiments creating many-body entangled states. The experiments in optical lattices using controlled collisions, both in Munich, but also the work here. Some years ago using controlled exchange interactions, and a number of recent experiments creating entangled states of 40 atoms in optical fiber cavity from Paris last year. This experiment using close to 200 atoms also uses Rydberg interactions to create many-body entanglement. So there have been a lot of successes in creating large entangled states of many atoms. These are not really qubit experiments. You can't identify qubits in these works. And my main focus will be in actually using qubits and thinking about circuit model quantum computation. So another way to look at developments in the field is to look at how many entangled qubits people have achieved using different approaches in the last couple decades, with the first quantum jump experiments with a single trapped ion in the mid-'80s. And there's certainly been an upward trend with a number of different platforms. Innsbruck has had 14 entangled ions. Maybe Chris has more. I don't know that it's been published yet. But there's an upward trend in a number of technologies. The neutral atoms are still down here at 2 qubits. And I'll try and convince you that I think we're going to be able to push that number up quite a bit in not too long. And how does one scale up? Well, classically, in classical computing, there's sort of two paradigms for scaling. One is to connect together many small processors, many cores, and the other paradigm is to build a single, very powerful supercomputing device. Also, in the quantum world, you see the same paradigm. There are architectures for scaling up by connecting many small systems. So Chris Monroe and Jungsang Kim's architecture from their music project of connecting many small ion traps using photons. Demonstrations have been done with single atoms in cavities, for example, in the Rempe group. One way we're thinking about this is building a very large atomic qubit array. And I'll argue that 10 to the 4th qubits is not an unreasonable thing to imagine. So we're approaching this goal of creating large-scale entanglement and useful entanglement using qubits in a number of different ways. In Madison, in my group and in collaboration with colleagues, we have 5 different experiments going. And I'll tell you about a couple of them today. We have an experiment with ensemble qubits, where we're creating entangled states of 10 to 20 atoms and working on entanglement between ensembles. We have an array of single atom cesium qubits that I'll tell you about. At some point, we want to connect together these two capabilities and include the possibility of coupling these ensembles to light efficiently and to make some functional quantum nodes. That's a new project that we haven't got too far on yet. As Chris mentioned, we also have other ideas for encoding qubits and ensembles using atoms with many internal states. Here, holmium atoms, one can in principle encode a whole register of qubits in one ensemble. So we have a project going on that. And I'll also mention a project to couple atoms to superconductors using, by putting cold atoms into a cryostat. I know there's very closely related work going on here, so I'll give you a progress update on this thing. So everything we're doing in my lab takes advantage of strong Rydberg interactions. So just a little bit of background on the Rydberg interactions. We know that ground state atoms interact very weakly. If we take those ground state atoms and pop them up to a Rydberg level, we get a very strong interaction. And the difference in the ground-ground and Rydberg-Rydberg is just enormous, 12 orders of magnitude at length scales of about 10 microns. And that strong interaction can be used to mediate entanglement. And indeed, atom-atom entanglement's been achieved in Madison, Institut d'Optique, recently at Sandia, also in Munich. Atom-photon entanglement mediated by Rydberg-excited atoms has been demonstrated in Alex Kuzmich's group. And a lot of people are working on using Rydberg-excited ensembles to implement photon-photon entanglement. That's not been achieved yet, but there's a lot of people trying to do that. So the observation of strong Rydberg interactions actually goes back a long way. This is the first paper I'm aware of from the Hirosh group, who reported on spectral line perturbations due to van der Waals coupling between very excited atoms. And this was in a sample where the average interatomic distance is 15 times the Rydberg atom radius. So the wave functions of the Rydberg excited electrons are not overlapping, but that will disappear in a second. But the atoms are interacting strongly. And you can see this from their data here. There's a low density spectroscopy of some Rydberg levels. At high densities, they see very substantial line broadening. And here's a plot of this as a function of 1 over r cubed, showing this strong splitting of the lines. So the mechanism behind that interaction is what we call a Förster resonance. Imagine I excite 2 atoms to s orbital momentum, angular momentum states. These are states of definite parity. There's no dipole moments, yet nonetheless there's a strong dipole-dipole interaction. And that's because there's strong electric dipole-allowed transitions to these neighboring states, where one of the atoms hops up and the other hops down. And if the energy of this upper state plus the energy of the lower state is equal to the energy of 2 of these states, then you have a resonant process. And that resonant process gives you a 1 over r cubed interaction. In practice, there's not perfect energy match. There's a small energy mismatch, a Förster defect. And so at long range, the 1 over r cubed goes over to 1 over r to the 6. So here's a plot of that for the 43D states in rubidium, where you have a relatively small energy mismatch, just a few megahertz, and you get a strong interaction. The scaling is tremendous. So the van der Waals scaling at long range is generically n to the 11th. It turns out in the heavy alkalized rubidium and cesium, the difference in quantum defect between the s and the p states is almost exactly 1/2, and that kicks you up to an n to the 12th scaling. But either way, you have this tremendous scaling with n. So going to high Rydberg numbers, order 100, we get this 12 orders of magnitude increase in coupling. Okay, and indeed that coupling's been measured directly. So here's a very nice experiment from Antoine Broet's group from a couple of years ago, where, not really a surprise, but it was reassuring to know that they could measure these energy shifts for different Rydberg states, and the measurements agree extremely well with ab initio theory. In fact, I like this because I could go and check my own computer code and make sure that I was calculating correctly, and indeed we get the same numbers. Okay. And it was shown some 15 years ago in what are rather old papers now, how to use that strong Rydberg coupling to create entanglement. You can tell these are old papers. There's no fancy color 3D graphics, just black and white drawings. But these papers have led to a whole field of people working on trying to use Rydberg interactions to create entanglement. And so my outline for the rest of the talk will be to first tell you about our work in ensembles, where we're now able to verify that the states we create using Rydberg interactions in one of these ensembles are indeed entangled states, and progress towards entangling 2 different ensembles. I'll then tell you about what's going on with this array of single atom qubits, and at the end, progress towards entangling atomic and superconducting qubits. So let me start with the ensembles here. So there's a lab somewhere down here. There's some ensembles. And we're working with rubidium atoms here, order 10 or so atoms in dipole traps with about a 10-to-1 aspect ratio. So the transfer is about a half micron, about 5 microns long. These are the students working on this, and it's a long-standing collaboration with Thad Walker. So one thing we might do, starting to look at many-body states in this ensemble, is just optically pump all the atoms into one of the hyperfine levels, m equals 0 Zeeman state, creating this spin-up product state. And so that's easily prepared with optical pumping. How do we get more interesting states out of this? Well, one thing we might do is just rotate those spins. So we turn on a microwave coupling the two states, and we'll create a state which is the rotation operator acting on each of the initial spins. If we do that, the state that we create is a superposition of states with up to n spin excitations. The probability of obtaining just a single excitation after that rotation is given by this expression here. And if I calculate the overlap onto the singly excited state, it maximizes at 1 over e for n large. So that's the best I can do in terms of creating the singly excited state just using a microwave rotation directly. And so here's an example of data showing that. We measure the number of spin excitations using a push out of the 0 states and then measuring how many atoms are remaining. And if I start with no rotation angle in the 0 state, then the probability of observing 0 excitations is large. There's a little bit of a gap here because when we do this blow away, we have a % or 2 error of atoms falling down to the other level. But as I rotate, the probability of being in 0 goes down. The probability of being in 1, this yellow curve, goes up, and then greater than 1 correspondingly comes up. So we can create different spin excitations just changing the rotation angle. Why is that interesting? Well, it's interesting because the state we're creating is not this state, but a superposition of any one of the atoms being in this spin flip state. And this is a many-body entangled state, the W state. So if we can measure a spin excitation non-destructively, then we can prepare this entangled state without any local control of the atoms. And that can be done probabilistically with a best 37%. And indeed, that was done by Jakob Reichel's group last year with up to about 40 atoms. What more can we do with Rydberg blockade? Well, using Rydberg interactions gives us the potential for not creating this entangled state probabilistically, but creating it deterministically. So if I start with all my atoms in 0 again, pi pulse up to Rydberg, and then down to the other spin state, because of Rydberg blockade, I only get a single excitation here. So in principle, we can deterministically map onto this many-body entangled state. And the coupling strength scales as the root of the number of atoms involved. Okay, so here's an example showing some data from last year, showing this root n scaling of the coupling frequency. You see these Rabi oscillations getting faster and faster. And we can plot the observed frequency versus the mean number of atoms in the ensemble, and you see the root n scaling that you expect. And this has also been done for larger numbers of atoms some years ago by Alex Kuzmich, and more recently in Munich, going up to several hundred atoms. So this root n scaling is well established now. We can also check the coherence of these W states by doing a Ramsey experiment. And we see coherence times of a few milliseconds, depending on the number of atoms in the ensemble. And we can plot the coherence time, or T2 star, versus the mean atom number in the ensemble. And this plot shows data from two different types of preparation experiments. This blue data is from product states, where we just do a microwave rotation on the ground hyperfine levels. And the red data is where we use the Rydberg interactions to create these W states. And if you look at the single atom data, so this is just looking at coherence of one atom in a superposition of the two ground states, the microwave prepared state has a longer coherence time than the Rydberg prepared single atom. And that difference is an indication of our laser quality. The clock, the phase reference for these Ramsey experiments is now the phase coherence of our Rydberg lasers. And this difference here you can attribute to the several hundred hertz line width of the Rydberg lasers. So that's why this is lower. And then we see this kind of 1/n scaling, which is consistent with collisional dephasing of these W states.
On the previous slide, you said there was something about the Ramsey contrast, but I didn't catch it. Can you?
I just was saying that that's how we extract our T2 star, I think. I will come back and talk about this.
But I guess the question I'm asking is, how good is the contrast? That's what
That's a key question, and I will address that in more detail. But it's about 50%. The best here, the best we've seen is pushing 60%. And that's one of the issues we're struggling with.
So you're going to tell us about
I'm going to tell you about that. Yes.
Okay.
Okay. Let me skip these slides. This is just saying quantifying many-body entanglement can be difficult. But the question arises, how do we know we're really creating entangled states in these ensembles? And indeed, one can simply use the amplitude of these Ramsey fringes to prove that we have an entangled state. And this is adapting ideas from this Reichel group paper. So if we look at these Ramsey curves, these are 3 curves for different delay times. We see a non-excited probability, here 44%, the probability of exciting this state, and then a missing bit here, which we can attribute to singly excited but orthogonal to the W state probabilities. And if we assume perfect blockade, that we never have more than one excitation because of Rydberg interactions, one can show that the number of atoms K in the n-atom ensemble that are participating in the entangled state is bounded by this ratio, which is related to these Ramsey amplitudes. And so we can show that we have something like 80% of the atoms participating in the entangled state. We don't have to assume perfect blockade. We can check with a Monte Carlo study, but then we don't have a nice analytical expression. So this gives us strong confidence that we're indeed creating a many-body entangled state. Another way of verifying this entanglement is to rotate the W state. And this shows a calculation of what one expects to observe if I prepare a singly excited state and then rotate it with a microwave between the hyperfine levels. This shows the probability of observing no excited spins. And if I prepare the W state, there's 1 excitation. So if I don't rotate it, that probability is 0. As I rotate it, I would get this blue curve. And I can contrast that with the singly excited state, which has 1 excitation, but has no entanglement, this incoherent state of the n spins, which would give me this dash yellow curve. So we've done this. We prepare the W state as best we can, and then rotate it with microwaves. And you see this little bump in the P0 probability, and that bump is indicative of the W state. And we can make estimates as to what is the fraction of the W state, what's the fraction of other states, and see how that those ratios change as we change the delay time. That is, we wait around for the state to decohere. That would be the difference between this blue curve and the red curve. So this is an alternative to the Ramsey amplitudes to do a kind of rotation tomography on these states to look for entanglement signatures. So I'll now tell you about ensemble-ensemble interactions, and this will feed back onto understanding why we're not seeing 100% preparation of these W states. I can use Rydberg blockade to interact these 2 ensembles. If I excite a single Rydberg in one of these ensembles, I can see if that excitation will prevent excitation in a target ensemble. And that blockade interaction is the key ingredient for then creating entanglement between these 2 ensembles. So this shows an experiment where if I do not excite the control ensemble and just rotate the target ensemble via the Rydberg level between its 2 ground states, I see this red curve. And in this data, this comes up to about 50%. If I instead first Rydberg excite the control and then try and do this, I get this black curve down here, which is suppressed down to about 11%. And indeed, if we post-select this data on the successful excitation of the control ensemble up here, then we see essentially 0 rotation of the target ensemble. So the blockade strength between these 2 ensembles is very strong, close to 100%. And what we can deduce from this 11% here is that with at least 89%, we're able to excite the control atom to the Rydberg level. Nonetheless, when we do this rotation on the target ensemble, it doesn't come up to 89%. It saturates around 50 to 60. Why is that? Well, one thing we've looked at is varying the strength of the interaction. So we've done some experiments with 3 ensembles, so a third one even further away, having a weaker Rydberg-Rydberg interaction. We've also varied the principal quantum number at the level, looked at 97 and 111. And what one can see is that as the interaction between these two ensembles gets weaker, then we have a little bit of secondary Rydberg excitation, a little bit of double excitation, and that apparently dephases the rotation on the control ensemble. So in this experiment, we're Rydberg exciting here, doing a rotation by an angle theta and one of the targets, and then finishing the rotation on the control ensemble. And what we see is that the probability for the control ensemble to end up in the W state, the normalized probability, decreases as we go to weaker and weaker interactions. So as we go to weak blockade, something happens to our ability to manipulate the control ensemble, and we might attribute that to some kind of double excitation giving dephasing. Indeed, we can take these 3 curves and plot them on a universal curve with a reasonable degree of success, where this function f is basically proportional to the probability of a double Rydberg excitation. So the larger the probability of doubly exciting 2 Rydbergs, the more we disturb the rotation of the control ensemble. So that says we need to be very pure in terms of only having a single Rydberg atom excited at a time. And when we're inside a single ensemble, we have a very complicated situation, in fact. The atoms are not uniformly spaced. There's large separations, small separations. If you calculate all the molecular energy curves at small separation, you see a veritable spaghetti of overlapping molecular curves. And that is possibly, although it's certainly not been figured out in detail yet, that's possibly part of what's behind the lack of success in creating these W states with very high fidelity. So there's some recent theory work by Andrei Derivianko, Misha Lukin, and co-workers pointing out the possible influence of molecular resonances in ensembles where you have variable atomic spacings. So what we're engaged in right now is adding a background lattice to this setup to limit the short-range interactions. And our next step is going to be to repeat this experiment with the lattice in place, and we'll see how that comes out. So although one can indeed create entanglement in these systems, there's still open questions as to what exactly is limiting the success rate. So that's about ensembles. Let me move on now to this array of single atom qubits, where in principle we have a much more controlled, less randomized situation. So again, there's a lab, and there's a table here where we have a small vacuum cell and optics for addressing and controlling a 2D array of atomic qubits. So the basic experimental setup starts with a 2D MOT. We push atoms up into a chamber where we make a 3D MOT. So we turn on our cooling beams. And then we project an optical lattice onto the 3D MOT and load single atoms into these sites. And this is a somewhat unusual lattice design. It's a intrinsically 2D array of 3D traps which localize the atoms in 3D. And we do this without phase-sensitive interference between the beams. It's a lattice which is simply projected in through one lens. And so we have a 49-site array of single atom qubits. This is a composite picture. We don't load every site in one go, but we have up to 49 sites. And then we have a number of beams for doing Rydberg excitation and ground state rotations that we can address onto individual sites using acousto-optic scanners. So here our qubits are the m equals 0 cesium clock states. Okay, so here's a picture of readout, again a composite picture, but showing that one can very well observe single atoms at all of these sites. The loading rates vary a bit from site to site. On average, we can hit about 60%. Individual sites can be 70% or sometimes even a little bit better, with essentially zero overlap. So we can really see these single atoms with high fidelity. The experimentalists in the room will appreciate that you don't just turn the apparatus on in the morning and it looks like that immediately. So there's a lot of optimization that goes into this. And one of the tools we now use standardly was developed by Marty Lichtman. I'm sorry to say he's now a postdoc here and no longer a grad student in my lab. But he developed this very nice multivariate optimization software that uses a Nelder-Mead algorithm on a large number of parameters to tune in whatever cost function we want to define. So here we're plotting a cost function which is minus the loading rate, so the fraction of sites that get loaded with an atom, times the retention fraction of those atoms after a measurement. And we run these things overnight sometimes, but here you see it takes about 3 hours to go from a nominal state to this state close to, say, 60% loading. So this is very useful classical software.
So Mark, when you say 60% loading, that means that of the 49 sites, that 60% have an atom.
That's correct.
And so what was the meaning of the fact that some individual sites are 70? You mean that there are some that are better on average that you can...
Sure. So if you look at these graphs, say this one atom peak, that's the background, that's the one atom, that's got less area in it than this one. So there's some variation site to site. The best sites are above 70%.
Okay, and that's basically ones that are at the center, or what?
No. So this projected lattice has some complicated optics. It's not perfectly uniform. That's maybe the downside of not using interference. And so there's some site-to-site variations. There's also site-to-site variations from our Mott beams, the usual phases from retroreflected Mott beams. Other groups have shown that you can push the loading in a single site or a couple sites up to above 90%. And we've tried some of those techniques, not yet with success, but we believe we should be able to push this up to 90% also. But we've seen 70% or more. So here's an example of a high loading site. Okay.
But just to make sure I'm understanding, though, the way you're loading this thing is you're looking at everything.
Yes.
And you're conditioning what you do based on what you see. That is, you load things, you can see them, but you can retain them even after they're scattered photons, and you
That's right.
see that they're there, so you can say, okay, let's keep loading, this one's empty, let's keep going, or whatever. Is that the idea?
Yeah, that's a very good question. Let me be clear about that. In an actual experiment where we're doing qubit operations, what we do is we load up the whole array, we take a first picture, we identify which sites actually have an atom in them, and then we perform our qubit operations and take another picture, and we only keep data from sites that had an atom initially. So this retention number, which can be 2 nines or better, is the probability that when we look a second time, we still have an atom.
So one final question. So with 70%, that means that almost every atom where there is one, there will be a site either in X or Y that has
Sure, that's
another
right.
one.
That's right.
Because ultimately you care about pairs, right?
Ultimately, we care about much more than pairs, but yes. We care about having a useful number of atoms within an interaction zone of one of them. And so the higher the loading probability, the larger zones you can work with, right? Supposing I want to make a logical qubit with, say, 10 atoms, then I want the loading rate to be high such that I don't have to repeat many times to get 10 atoms at once. Sure. So we believe we can get that number well up over 90%. That's not the limiting factor for us right now, so we haven't put our main focus in that direction. So here's single qubit rotations using microwaves, just globally applied. Again, it's a composite picture, but it indeed shows that you can rotate all of these qubits and measure them individually. And so this is just going for long times, out to about 5 milliseconds. For quantum computing, we need to do single qubit rotations on single sites at a time, and we perform that with a combination of the global microwaves and a focused optical beam coupling up to the second resonance level of cesium, which Stark shifts just one of these sites at a time. And we can either put the microwaves on resonance and Stark shift a single site out of resonance, or we can detune the microwaves and locally Stark shift into resonance. So this shows a locally addressed site with a Stark shifting beam and just a little bit of crosstalk on one side on the surrounding sites. We can also hit a number of sites at a time in one experiment. We have these 2D acousto-optical scanners on the beams, And using profiles on a DDS generator, we can hit a number of sites in one experiment. Okay. So we've done randomized benchmarking to see how well these gates perform. And we can look at average numbers over the entire array when we use microwaves. And we can get close to 3 nines of fidelity, and on the best sides, 4 nines. Also, fidelities for single site addressing with the Stark shifting beam, which are a little bit over 2 nines. And so these results are near fault tolerance thresholds. They need to be improved somewhat, but this we have good confidence that we can get these single qubit gates to high fidelity. So what about the 2 qubit gates? That's the more difficult challenge. So here's the old Jack et al. Protocol. You excite a control atom, you do a conditional 2 pi on the target, return the control atom to the ground state. The gate fidelity is optimized by working in the sweet spot where the error due to spontaneous emission from the Rydberg levels plus the error from imperfect blockade is minimized, giving you a fidelity that scales inversely with the product of the interaction strength, the blockade strength B, and the Rydberg lifetime tau. Okay. So ideally, this sequence of pi, 2 pi, pi gives you a controlled Z gate. So we have a 1 and -1s. Reality is a little bit different. And that's because there's various Stark shifts we need to take account of. So we have a 2-photon excitation to a Rydberg level, and these photons have resonant Stark shifts, which cancel each other when we're tuned close to the intermediate level, but also each of the beams provides non-resonant Stark shifts. So this omega-2 beam coupling a p level up to a Rydberg level also has a non-resonant Stark shift on the ground state. This beam here has a non-resonant Stark shift on the Rydberg state. And so there's a lot of Stark phases floating around that we have to keep track of. And not only the Stark phases, but in fact the 2 pi rotation can give you something that, at least to me, was quite surprising. So the basic phenomenon that's being used in this Rydberg entangling gate is the fact that when you rotate a spin 1/2 or a 2-level atom by 2 pi, you pick up a pi phase. It's a basic quantum mechanical phenomenon. We're not doing this experiment with a single photon, we're doing it with 2 photons. And when you do a 2 pi rotation driven by a 2-photon transition, you get pi plus a bunch of other phases. You're not guaranteed to get pi. And these other phases are due to the resonant and non-resonant Stark shifts on the participating states from the beam. So we have to set these phases correctly or compensate them to get high fidelity entanglement.
Mark, that extra phase is just a detuning factor, right?
Well, yes and no. So the thing that was surprising to me is that even though we're 2-photon resonant, you do not get a pi phase. That to me was a surprise.
But that's because of the single photon shifts, is that?
That's correct, but I mean, naively, and
Yeah.
I can be naive, if I'm 2-photon resonant, I thought, fine, we get pi, but you don't.
But you would if everything else was really real far from resonant, right?
These are not 2-level atoms, and so you have these off-resonant Stark shifts, which matter. If it was a 2-level atom and you were very far, or a 3-level, very far from resonant, you'd be
Right,
okay.
Like if this had been 1s to 2s in hydrogen, it would be pretty close to the.
Yes, yeah, that's right. Yeah. So we've done the detailed bookkeeping of all these phases, and you don't get this ideal controlled Z matrix. You get something with 4 different phases on the diagonal, or I can factor 1 out and have 3 phases I need to think about. So fortunately, it turns out that if you set the gap time correctly between these pulses and the 1-photon Rabi frequency ratios, you can indeed recover an ideal entangling gate. So it says here when this phi BL is small, this is the residual blockade phase shift, and that also can be compensated, so that's not an issue. So up to single qubit rotations, we can indeed get what we want. So here's the protocol for 2-qubit entanglement. What we're doing is putting a phase shift on the second pi by 2 rotation after the controlled Z gate, and that creates, in principle, maximally entangled states, but they're not Bell states. They just have non-standard phases, so they're superpositions at Bell states. So we're doing this with the blockade interaction to give you a sense of how strong the interaction is. We're working at 82S. Here's the curve of 10 megahertz interaction for 80S, 100, 120. So with this 4 micron lattice spacing, we can in principle entangle a substantial number of atoms. In fact, you can do quite a bit better than this. This assumes exciting both atoms to the same state. If you excite the atoms to different Rydberg states, you can get much stronger resonances and push these curves out quite a bit further. Okay. So here we've picked 2 of the states. We're doing 2 photon excitation up to S states for this data. And this shows that we can Rydberg excite on 2 separate states with minimal crosstalk on nearby states. So this is 82S, giving us 20 megahertz coupling.
So what's your contrast there?
So this is starting in the ground state, going to Rydberg and back to ground. This number should not be seen as failed excitation, but rather as the fact that our Rydberg detection is not 100% efficient. That is, we can excite a Rydberg atom and not lose it, and therefore these curves don't go to 0. The important thing is that they come back to 0 here. We don't lose the atom.
So those are effectively 100% contrast or near 100% contrast. It's just
We
you're not
claim
seeing
so.
that because of this detection issue.
That's our claim, yes. We don't have an ion detector in this chamber, so we have to indirectly ascertain Rydberg excitation by these loss measurements or by the blockade we see on other atoms, and that's why we think we have 100% excitation. So as I mentioned, one has to control these gate phases carefully, and to do that we need to know our Rabi frequencies. And so we calibrate them using a sequence of spectroscopy steps. We need to know the Rabi frequencies, we need to know the detuning from the intermediate level, we know the detuning from spectroscopy. To get the first photon Rabi frequency, we do a Ramsey experiment with that light, and we know the matrix elements, so we can calculate the field strength. We then do a ground to Rydberg Rabi frequency measurement, which depends on the product, omega 1, omega 2. That now tells us omega 2. And then we set parameters to tune the differential Stark shift of the ground and the Rydberg levels close to 0. This inset shows a ground Rydberg Ramsey curve where we have a couple megahertz differential Stark shift. And this shows very slow changes when we tune in close to 0, which is where we want to be for the gate. So here's the C0 sequence, state preparation, probability matrix. This shows if we blockade or do not blockade, we get this pi phase shift between the curves, which tells us that we are seeing Rydberg blockade. And the probability matrix has an 80-some% overlap with the C0 matrix. And we check fidelity using parity oscillations, and we come up to 73%. So I'll talk some more about this number. What we're working on right now is trying to extend this to a 3-qubit experiment. We're looking at Grover's algorithm, picking 3 nearby states. And one of the nice features of this Rydberg blockade interaction is that you can implement multi-qubit gates very efficiently with a small number of pulses. So instead of decomposing the Foley operations or multi-qubit operations you need for n-qubit Grover into 1 and 2 qubit gates, you can directly implement these multi-qubit gates in Rydberg interactions.
So I noticed on multiple of your pictures, your trap's not necessarily spherical. That's again just aberration in your optics?
This is probably aberrations in the traps in those cases, and that the probability distribution of the atom is not perfect. It's leaking around a bit. Yeah. So what's the status on these Rydberg gates? So a couple groups now have created entanglement using Rydberg interactions. I mean, there's also this old experiment from Paris, creating EPR pairs, but really using a very different technique, although they were Rydberg atoms. The what I'll call modern blockade experiments were first done in 2010 by us and the Granger-Broets collaboration. And first experiments were post-selected. So these open yellow circles are data from post-selecting against atom loss. That means that you measure a Bell fidelity, and then you assume that you'd have the same ratio for everything if you scaled it up by the loss probability on your atoms being there after the gate. So that gives you a post-selected number. We were able to edge over the true entanglement limit the next year using a slightly better apparatus, so deterministic entanglement. No one did anything for a few years. We then repeated in the array. This year, Grant Biederman's group at Sandia posted a better number using a slightly different technique, so a kind of Rydberg dressing method. And then we've been able to repeat the blockade gate with somewhat better data, now 73% deterministically. That's progress, but of course it's not up here where we need to be to build a scalable machine. And all of these experiments, the main contribution to the loss is not that the blockade does not work, the main contribution to the gate fidelity is not a failure of blockade, but the fact that people are losing atoms somewhere. And so I find this data informative, if not explaining everything that's going on. Here's data from a 2 pi rotation. So we start in the ground state, we do this 2 pi on one atom, we can come back to the ground state, and we can tune this point in right up to 1. So there's no loss. Then we do something else, which is we take one atom and we do a pi gap pi, and then we see if we still have an atom over here, and I vary that gap time. And even at very short gap times, pi gap pi is different than 2 pi. So we're missing 15, 20% here. And what's going on? Is it Rydberg state mixing? Is there some contribution from background electric fields, sharp edges, and the quasi-square pulses we're using for excitation? This is what keeps me up at night for a long time now, trying to understand this. And I'm optimistic that we'll work this out, but this is indeed still work in progress.
How's that zero? Isn't zero real zero just like what the left-hand picture? On the right graph,
Yeah.
the gap time being 0.
0 is as short as we can make it while turning the laser off and on. So it's
Okay.
100 nanoseconds or so.
Okay. But it involves like sending the light.
Yes,
down
right.
and
It's
back
not,
up.
yes, exactly. That's what we mean by that. Yeah.
And so not turning it off gives you 100%, and turning it off for 100 nanoseconds gives you 80%.
Yeah, that's right. So one thing we've been looking at, although I'm not going to talk about it today, is instead of using these quasi-square pulses, using shaped Gaussian pulses or more sophisticated pulses. There's certain advantages to that, and theoretically it shows the gate fidelity can come up to 4 or 5 nines, and we're working to implement that in practice and see if that makes a difference.
So when you don't turn it off, don't you still have edges?
You do, that's correct. That's correct, but you don't have an edge while you're in the Rydberg state. So there's a difference there. These edges, when you don't turn it off, occur when you're in the ground state. So there's something different. Okay. So to summarize what the status is on this array, we have very respectable numbers for loading, lifetimes, T1 and T2 times, which are long compared to gate times. It's this number that's most troubling, and we're certainly working on that to try and figure that out. Okay. Nonetheless, let me ask for your indulgence and speculate a bit about where you might go with this system. So again, there's these 2 paradigms. You hook together a lot of small systems, or you build one large system. What's reasonable to think about here? How many qubits might you put in one array? Well, we've made quite a bit of progress in Madison over the last 10 years, starting with our first 2-qubit experiments 5-6 years ago. We're now up to about 30 out of 49. We're building a new version of this, which uses an improved design for the trap light, which is about twice more efficient, and this should push us up to over 100 sites, and so 70 or so that we can anticipate. And indeed, there's been a number of experiments with single-site control now that are around 100 sites or more using neutral atoms. How far might one push these arrays? Well, there's some limits set by optics. If I think about a lens with a certain numerical aperture, illuminating an area where I have qubits of area A, then the resolution on one axis is basically lambda divided by the numerical aperture. This gives me an areal resolution, and the number of resolvable pixels will then be this area divided by that dA, which scales in this way. So naively, I would just increase A for a given lens numerical aperture and get more and more pixels. In practice, there's lens aberrations. You can't really do this, but let me take a realistic number, say a well-designed objective, not the state of the art, but a good objective, NA 1/2, an area of a square millimeter. That gives me 250,000 resolvable pixels. Let's be realistic and say I'm going to use 5 lambda by 5 lambda for each qubit, so I don't have too much crosstalk. That's about 25 square microns per qubit, 10,000 qubits. So I would claim that you could think about pushing this to very large numbers. Obviously, there's many challenges. You need enough optical trapping power. How do you do measurements in this large array? You need to scan your control beams, your control wiring. What about atom loss and reloading? We thought a lot about all of these challenges. We just wrote a big proposal and spent a lot of time thinking about these things. I could spend a couple days talking about it, but let me tell you about one aspect which I think has some interesting physics, which is this qubit measurement challenge.
So what are we actually looking at here?
We're looking at, what you're actually looking at is my real 4949 data duplicated on PowerPoint. But you're looking at 10,000. And this number is interesting. It's 0.14 square millimeters. It's got a small footprint. So one of the difficulties of these neutral atom experiments is the qubit measurements and doing them without crosstalk. So we like to cycle photons, say in cesium, from 4 to 5 prime on the cycling transition, but every now and then we get a Raman transition down to the other hyperfine state, which messes up our state detection. You can cycle about 40,000 photons before you get a Raman in cesium, but we don't do the readout on resonance. We'd get too much heating. We detune by about 5 gamma. Then this ratio shrinks to about 3,000. Okay, but if I have fast optics and a reasonable quantum efficiency, say 1/2 for the camera and the detection filters, then I can have a probability of no Raman being close to 100% after detecting 1 or 2 photons. So to have a low noise camera, I could in principle do this without having any Raman. There's another issue though in the array, which is crosstalk. Supposing I have pretty fast optics, 0.65 NA, 1/2 quantum efficiency, and I work with this 5 lambda lattice, then the probability of absorbing a photon in a neighboring atom when detecting one is close to 10%. That's a real issue if you're going to do error correction. And there's different ways you can think about mitigating this. Let me tell you about one idea which I think is interesting. You could do shelving. It's kind of complicated. Let me not go into that. Let me tell you about a 2-species idea. In fact, the ion traps have been doing 2-species experiments in the last year. Both Boulder and the Oxford groups have demonstrated 2-species entanglement now. And we're thinking about doing the same with Rydberg. So I want to imagine that I have this 2D array with cesium atoms being used for computation, and interspersed are rubidium atoms, which will be measurement qubits. And if I make my trap light 820 nanometers, then I'm blue detuned relative to cesium and red detuned relative to rubidium. And the way we make our 2D array naturally will give us cesium atoms in the dark spots and rubidium atoms in the bright spots. So it's a very straightforward way of making a 2-species lattice. Now, if you remember the Rydberg interaction through this Förster mechanism, the point was that the energy separation here was close to the energy separation there. If you think about it, these don't have to be the same type of atom. They could be different isotopes, they could be different elements. And so I could, if I can satisfy this resonance condition with one atom being cesium and one rubidium, I can get a very strong interaction. So here's a plot of the energy defect for rubidium coupling to cesium for different fine structure transitions for S to P levels. And you see these resonances where the energy defect goes very close to 0. You get a very strong interaction. So rubidium 84, cesium 89 gives you 50 megahertz at 10 microns. Very strong. So we want to use that to do measurements. And the idea will be, instead of trying to directly scatter photons off of this atom, I'll couple the quantum state of this atom onto the state of neighboring atoms. And I can do that because I can achieve a ratio of the cesium-rubidium to the rubidium-rubidium coupling in this array of something like a factor of 50. And that means that I can, with high fidelity, map the state of one of these computational qubits onto the state of multiple rubidium qubits. I'll get a faster readout, And then the light scatter from the rubidiums will not affect my cesium qubits. So we're setting up a first experiment right now just to try and entangle one cesium with one rubidium atom. And I think this has a lot of promise for doing readout in large arrays. And then there's a bunch of other challenges, but all in due time. So let me end up in the last couple minutes and tell you a little bit about what we're doing on trying to entangle atomic and superconducting qubits once more using Rydberg interactions. So there's a little Mott apparatus in the vacuum chamber there. So another way to think about figures of merit for quantum information towards scalability is looking in the space of coherence time and inverse gate time. And different approaches are optimal on different axes. So ions and neutrals have very long coherence times, but their gates are not as fast, their entangling gates are not as fast as superconductors and quantum dots, which have much shorter coherence times. Certainly we could combine a couple of these, we'll get perhaps closer up to this upper right corner where we want to be. And that kind of hybrid interface could also let us imagine things like coupling fast processing and superconducting qubits to neutral atom memory that also can couple to photons and create a larger quantum network. So we'd like to do this using Rydberg interactions. Now, and we'll do that not by directly coupling to superconducting qubits, but by coupling to microwave photons, which in turn are coupled to the superconducting qubits, a capability which the superconducting community has excelled at in recent years. So we'll confine a microwave photon in a small volume on a coplanar waveguide resonator and think about coupling that photon to some atomic transitions. Well, there's the ground hyperfine transition where a qubit is stored, and that, depending on the atom, has frequencies compatible with the frequencies in these circuits, but it's a magnetic dipole transition and hence is weak. On the other hand, if I can pick Rydberg levels where I have the same frequency separation, these are now electric dipole transitions with very strong coupling, large matrix elements scaling as n squared. And so this approach has been developed here at JQI. It's also being worked on in Vienna. One gets coupling strengths, depending how close the atoms are to the resonator, of some tens of hertz per atom, pretty slow, so you want to use a whole ensemble of atoms. If we go up to this electric dipole coupling up here, we can get something like 40 megahertz per atom. And so the Wallraff and Merck groups in Zurich, Fortag in Tübingen, and us in Madison are trying to do this. And so here we pick up 6 orders of magnitude. Not the 12 orders of magnitude that we had for the atom-atom coupling, but still a substantial number, and enough that we can think about trying to do this with one atom instead of an ensemble, and thereby hopefully mitigate some of the challenges with light scattering onto the superconductor. So this is our protocol for creating entanglement. We excite the atom up to a Rydberg level, and there's a conditional 2 pi rotation in the Rydberg manifold driven by the presence or not of a microwave photon, and then we bring the atom back down. This is different than the atomic entangling gate. This is not a blockade operation. It's just a direct interaction in the Rydberg levels. You can put in numbers and imagine that you could get several 9s of fidelity with resonator Qs at 10 to the 5th or so. You do have to be in a dilution fridge to beat down the thermal background. So our technical approach, although we will need a dilution fridge, is to start with a 4K learning environment. So we have a 4K flow cryostat. We have a chamber bolted on the bottom. And then we're going to make atoms in here, optically transport them over to the resonator, and Rydberg excite them. So we've made some novel resonators for this work. In order to enhance the coupling strength, we build essentially a capacitor onto the end of the resonator, and then we're going to put the atoms inside this capacitor and shoot the beams through from the side. We've measured Qs of 10 to the 4th at 3 Kelvin. This should go higher when we go down to millikelvin temperatures. And we also have some electrodes here for field cancellation. So this shows calculations of the coupling strength, shows that you can get about 1 megahertz of coupling at 20 microns from the surface, which should put us in a strong coupling regime. This is actually without the 3D gap capacitor, which we estimate gives another factor of 10. So we might be able to be tens of microns from the surface, which will help. So the transport, we have a small Mott assembly in the chamber. We then grab it into a red dipole trap. We move over about 4 centimeters and then transfer into a blue trap. And then we're going to push that up right under the resonator. This shows single atom measurement in a blue trap. And then for the Rydberg excitation, we're using a somewhat unusual scheme here. We're going through a quadrupole transition, the first D level in cesium and then up. This has the nice feature in that there's very small Doppler mismatch. So if you counterpropagate these two beams, you have small sensitivity to temperature, and we're hoping this will reduce the need for substantial cooling inside the cryostat, which will be difficult. And this shows data from spectroscopy of a Rydberg line using this excitation scheme. And so this is very much work in progress. We just got our first Mott inside the cryostat, and we're now working, so this data is taken outside the cryostat in just a standard chamber. We now have cold atoms right next, in the cryostat, right next to the resonator. And so the next step will be to move the atoms closer and start looking for coupling. So to summarize, I think I'm out of time. I've told you about work with ensembles, creating entangled ensembles, observing strong blockade between the two ensembles, work on single atom qubits in an array, again, creating entanglement and trying to push that to higher fidelity, and progress towards entangling atoms and superconductors. And so us and many other people are working on these Rydberg-mediated entanglement schemes. The Rydberg interactions give you tremendous strength in the coupling, but they're not two-level atoms. They're complicated, and it will be interesting to see if we can overcome all the complications and really make these things work. Let me conclude by thanking the people working on this, these guys on the Ensemble experiment, these guys on the cesium array, and the superconducting experiment. And thank you for your attention.